extremely happy to be there tonight and with all of you. Actually, it's really great to have this huge gathering around this quite quite key topic. And thanks, Alex, for the very the great introduction. I think that was really also really a nice way to bring the thing on the table. What we want to present you in this presentation is really about first me introducing you a little bit what is the platform that we have there at Pictera, and then Roger will jump on more details, actually really diving into specificities. I'm Franck de Morsier, so one of the two co-founder and the CTO at Pictera, and Roger.
And I'm one of the computer vision scientists / machine learning engineers at Pictera.
So let me, go to the next slide. Yeah, so Pictera, we are based in Switzerland, so next to Lausanne. If you've ever been around in the place, so there's the lake side nearby, and so we are actually just close to the EPFL campus, and so having a quite nice spot there, close to the university, and in a nice, let's say, environment. In the team that is quite growing, actually, we have really a nice complementarity. So, of course, machine learning expertise and computer vision, strong computer science, and also some web expertise. And on the side also of marketing and sales engineering, we have now a team covering really all these aspects, and we keep growing. So we're really happy to keep in touch with all of you, and we might cross further each other along your career path potentially. If I would have to really summarize a little bit the Pictera platform, the main element around it is that it's an intuitive interface that allows you to create and train deep learning models in the most efficient way. What I mean by that is that you are able then to quickly spot where a model is performing well or poorly, and then you can start to improve it to reach the accuracy you need. The idea is that there's no really upfront cost, so you can really easily estimate the cost in advance that you will need for a given project. So you'll start to build and really improve your ML assets over time. So the idea is that you can have a shared library across your organization that everyone is basically improving over time. And the key things also to stress is that you don't have to care really about your IT infrastructure. So the idea there is that you can start small, then you can make things scale really at country scale. For instance, there was this mention of the Danish article. We'll come back to it. And there you don't have at any time to think about the IT infrastructure, about do you have the latest GPU. So all of this, we are basically scaling it for you automatically. And then finally, through the platform, you can also get direct access to satellite imagery and then really get the information extracted as soon as the image is made available. So the idea is that now really building up monitoring application is really available to all. So more technology aspect of things. So we are basically on one side enabling you to connect to your different data. So you can, of course, upload your own imagery, but you can connect to external servers like WMS servers and access, as I'm mentioning, either archive satellite imagery or task some new satellite images. And we'll come back to that after or so. That is something that we really recently released, and that really opens up the door for many monitoring applications. On the side of really the machine learning technology, there, as I was mentioning, there's this interface to allow you to adapt model quickly until you reach the accuracy you need. And we know, I mean, creating a machine learning model is always a journey in itself. And we strongly believe that this has to happen in an iterative way with interactivity, in an active learning fashion, basically, where you start to provide few training examples, you preview the outputs, you iterate by adding further representative examples and counter example. And with this idea that actually training a model, getting previews is only like a few minutes, up to 10 minutes, that allows you to really do quickly iterations. And Of course, along the way, you have basically access to a certain number of accuracy scores that allows you to understand a bit how your model is evolving, and also allows you to choose the right settings on your way. And important to be mentioned, I mean, you've probably already manually annotated some of your imagery, or you have done this kind of heavy labeling task. This is also something you can directly import into your model to start from there and to build on your past efforts, basically. On the side of basically transfer and low-shot learning, so this idea that you can beneficiate from pre-trained detectors that we are having, and then adapt it to your specificities. So we have a library basically of pre-trained detectors. It's really basically the idea that it speeds you up in your training of your deep learning model. It boosts the accuracies basically, because you are then only adapting the model to the specificities of your resolution of your sensor, or some specificities of your object. So you find there in the categories what is closest to your object of interest, and you will see there's like 30 models that you can choose from, different applications, different industries, and also different type of sensor resolutions you can choose from. Let's do a small exercise and imagine what would happen if you could get imagery basically extremely easily over many small area of interest. Imagine being as small as 1 kilometer square, that you want to start just by spending a few dollars and not more at the beginning, and then scaling things up. And then monitor these areas and see how they evolve, for instance, over the next couple of weeks, or even over the course of a day. Imagine that you could even see traffic coming in and out of a certain given site, or that you want to track illegal mining, for instance, and that then you're really able to act in near real time, so that you're really having a very short time from the image acquisition up to taking an action. Actually, this starts to be there, and so there's really this, let's say now, maybe a limit on the imagination and the application, because we have really now this possibility to search our imagery, to order new imagery, and directly behind that, as soon as the images are made available, run one of your customized detector and create really powerful monitoring application. And the good thing is that tonight we have with us Matt from SkyWatch, and I will pass him the mic. I'm very happy to welcome him on stage, and that we'll add a couple of words about it. Matt, you're actually muted, I think.
Can you hear me now?
Yeah.
Fantastic. Yeah, thanks so much. So my name is Matt. I'm representing SkyWatch here today. We're terribly excited to be here and to be partnering with Pictera. Just really high level, a few words here. I mean, Pictera is a great example of how an artificial intelligence company is using and leveraging satellite data, and that totally aligns with our mission here at SkyWatch. We're here really to simplify access to Earth observation data for our users and really democratize and aggregate that data to enable new applications, new ideation, new solutions. So this completely aligns with our mission, and we're terribly excited to be partnering with Pictera. We're trying to simplify access to satellite imagery, and I know Pictera is on the mission to help simplify geospatial analysis, so it's a nice marriage between the two of us. And yeah, our common goal around simplicity, I think, is really important, because satellite imagery in the past has been quite complex and difficult to get, and this type of relationship, I think, is going to make it a lot easier for customers to receive satellite data and analyze it in a very efficient way. So we're really excited, and I'm available for questions after as well.
Thanks, Matt. We are excited, very excited too. And some of you may have heard about this integration of SkyWatch and partnership between the two companies, and you should definitely go and have a closer look and try it out yourself. Before I pass the mic to Roger, I just wanted to also announce you that what's also coming up on Pictera is this idea really to go a bit beyond just creating your customized models, but that you can start to really build workflows. So what I mentioned basically on having a flow of satellite imagery that then to which you can connect a detector and directly get basically monitoring reports, alerts, is something that will start to be possible, that you can start to basically play and put together. And that's really the idea, that then you are the one to set this up for your applications and for your specific basically business. So I'm happy now to pass the mic to Roger, that will dive in the deep learning side of things.
Hey everyone, I'm Roger, and I'll be talking to you today about some of the details behind the Pictera platform and this custom detector that you can build on the platform. So moving on, there's three main things that you can we. Cool. There's three main things that I'll be talking about today. The first is what architecture we actually use behind the scenes for our custom detector and why. The importance of using data correctly, and also some of the settings that are available with the platform. Before all of that, I'd like to preface this talk with a bit of a why machine learning. And I want to bring up one word here, which is generalizability. And the idea here is that machine learning, by definition, is generalizable, and that's really what makes it so powerful. The idea is that you adapt the data to the problem that you're trying to solve, and not necessarily all the time the architecture. Indeed, one architecture is capable of solving a lot of different types of problems depending on the data that you provided. And this is especially true and especially powerful with deep learning. And so that's why with Pictera, the focus is on the data and the ease of creating a good data set, as Frank said. And it's less about playing around with the architectural parameters such as batch size and the optimizers and all that, which is very important in terms of pushing the limits of deep learning in academia. However, in industry, you're focused more on your use case, and therefore that means focusing on your data. That being said, we still need to train at least one core model, right? And so what is that model behind the scenes in Pictera? Well, it is a unit-like architecture. And so the question is, why do we build upon unit? Well, this is very much related to what I just said about the importance being focused on the data. Unit has fewer parameters, it has less bells and whistles, it's much less complex, which makes it faster to train. And I mean both in GPU time spent training and also time spent experimenting with the architecture itself. And the bells and whistles are nice at squeezing out performance if you're doing deep learning architecture research. However, not all of us are doing that. And in fact, if you look at some competitions in the geospatial domain, such as SpaceNet, specifically SpaceNet 2, which is about building detection, the winners actually use UNet and not so much, for example, these more shiny, very complex architectures such as Mask RCNN. In fact, we just did an experiment on our platform recently. We uploaded all the training data of the SpaceNet 2 competition and trained it on our platform directly. And right now, we actually achieve a better score than the winners of the SpaceNet 2 challenge by quite a large margin, actually. The other nice thing about UNet is that with some smart post-processing, we can accomplish the tasks of both segmentation and object detection together, which covers already a wide range of projects and applications in the geospatial domain. And now I'm going to talk a bit about the importance of pre-processing the data. Again, shifting attention away from the architecture itself. So in particular, I want to talk about some of the peculiarities of geospatial data. Say in this example, you're trying to detect lighthouses, which is pointed to by the red arrow. This is kind of a typical geospatial image. And in this image, there is a lot more background than there is foreground. Now imagine you're sampling data from this image in a uniform, random way. Most of the time, you're going to hit a background object. And because the lighthouses are so sparse, imagine you have a model that learns just to predict nothing at all. In fact, you could say that this model is accurate because there are so few lighthouses that if you predict nothing, you are already above 90% accuracy just in terms of land coverage and predicting over the land. So how do you solve this issue? Because in fact, this is one of the problems we ran into in the very beginning, which was if the data was too sparse, the model would actually decide to learn that you'd want to predict nothing at all. So there are a few different solutions, and they're actually simpler than you might think. Basically, you can just divide your training images into a grid of sampling probabilities based on object presence, and then just ensure that there is some ratio of background being sampled to foreground being sampled. On the right here, you see one iteration of one of these strategies that we tried involving a quad tree. And at the end of the day, it's as I said, it's just a grid with probabilities and counting objects. And it's quite simple, but it makes a huge difference in the performance of your models, more so than fine-tuning parameters of the architecture, as I said before. The main takeaway here is that you have to make effective use of the data that you have in order to minimize the amount of data that you need to create an effective model. I also want to note that we do some augmentations in the pre-processing of the data, namely random rotation augmentation and a bit of brightness and contrast augmentation. We don't do random scale or translation, especially scale, because typically you're working with training images that are at a fixed resolution, so you know the sizes of all your objects already. In case you aren't and you're working with a data set that has mixed resolution, we have a detector setting to help you with that. And I'll talk a bit about that later. These are all standard transformations, however, and the other neat thing is that nothing I've talked about here today is architecture specific. It's all about pre-processing of the data. And so getting into some of the detector settings, we do expose some ways for you to play around with the custom detector, but we do not expose, as I keep saying, the things like the batch size and the optimizer. We try to expose settings that we think really matter, which are validated by our internal experiment platform and also real-life use cases. I'm going to highlight 3 examples of these. The first is the size filter, which is very simple. Basically, it's just a setting that lets you filter out different sizes of objects in your output, and that already makes a huge difference in the performance of your model. The other one is training time, which might seem like something a bit more deep learning related, but in the end, it actually is more about the data. It's about how much data is being seen by your model. And as the number of annotations in your data set grows, you will probably want to increase that training time. The last one is quite interesting, which is detector resolution. And this is a pre-processing step. Basically, the idea here is if you have a data set that has a lot of different resolutions, then you can specify a spatial resolution for your detector, and it will automatically scale all the images in your training set to that specific resolution. And this is important for a couple reasons. The first is that if you have a mixed resolution data set, you could be seeing your object of interest at multiple different sizes, which means you're complexifying the problem for your model, because now your model has to learn, in this example, what a car looks like from different sizes. However, if you make them all the same size, that greatly simplifies the task at hand, which again makes the amount of data that you need become less and less. The other interesting problem, and this is a bit more diving into the details, is that because we are training models on GPUs, there are certain hardware limits to how much data a GPU can see at a time. And that can be expressed in terms of a tile size. So basically, we're sampling over your training images with fixed tile sizes because that's the maximum amount that your GPU can handle, or our GPUs on the cloud. And the thing here is that imagine you are trying to detect a building. And if you look at the image on the left, say this is a high resolution image, and the tile that you sample is falling only on this small portion of the roof. Now, you as a human, if you look at this sample, you would not be able to tell that it's from a building because you don't have the context around the building to understand that it is a building. You don't have the trees, you don't have the grass, the road, etc. Now, a deep learning model will have exactly the same problem. It needs that context to understand really what a building is. And so and this might seem like a simple fix, but the detector resolution setting comes in really handy here, because if you just downscale your imagery, then you can make a whole building fit inside one of these training tiles. And now all of a sudden, your model is capable of seeing the building and all the surrounding context, and will have a much easier time understanding what a building actually is. And so these are just a few examples of the settings that we expose for the custom detector. But the takeaway here is that rather than exposing all these little hyperparameters for the deep learning model, we want to expose the settings that actually matter, the ones that make an impact on your model. And so that was a bit more of a dip than a dive into machine learning, given the amount of time we have. So now I'll pass the mic back to Frank, who will talk about the applications and use cases of the platform.
Thanks, Roger. Yeah, now I just wanted to show you some also some concrete example after these more further explanation from Roger. So one thing to have in mind is that we have a quite large community of users that are creating custom detector for their application, and that's interesting to see that it's really ranging from ultra high resolution drone imagery down to free Sentinel satellite imagery. And one example that was mentioned before was this Danish example, and I wanted just to highlight it here a bit more. What's interesting there, I mean, the goal was to detect slurry tanks, which are water tanks nearby farms, and these tanks, they have really an impact actually on the environment because there's emission of ammoniac going out of it, and so they wanted to a little bit understand what is the effect of these tanks over the whole country. And actually, you see there also on a zoom view that you have the farms, the zone around the farms, which is these purple circles, and then you have these green dots, which are the detected slurry tanks. When you just zoom out a bit, I mean, you can see, I mean, there's like 34,000 farms spread all over the country. And in each of these farms, so there was slurry tanks detected, and it accounts for 26,000 tanks in the end. So when you look really at the full country level, there you really get a feeling for the size of the project. And to give you a sense also of how much data this represents, so it was 25 centimeter data, and that represents more than a terabyte of imagery. And the detector to detect these slurry tanks was actually built with just 56 annotations. And there, with a few iterations, they could reach the accuracy needed and really build the detector, the deep learning model, in a very efficient way. Just to show you also a different example of monitoring a corridor, a linear infrastructure corridor. So there, for instance, you can do this combination of having basically a flow of imagery coming and attaching to it a different set of detectors, like for instance, detecting different type of buildings, detecting vegetation. And these basically allow to plan maintenance, estimate, for instance, the risks, or set like mitigation measures if you want to, for instance, trigger alerts if there are threats in the corridor. And finally, to really even further unzoom and look at larger scale. So we are doing with the company SGS services to track basically tree logging at quite large scale. And there that's exploiting basically a Sentinel-2 free imagery and attached to that to a custom deep learning model for detecting these logging activities. And the idea is that once you have basically detections that are there, so extremely quickly after the image has been taken, there you can basically start to trigger the order for small AOIs, for these small detections with high resolution imagery. And you can start to characterize, validate what happened there, and understand a little bit about that activity of cutting trees. So very happy to pass now back to Geoawesomeness team, and I'm looking forward to hear the other presentation. So don't hesitate to ask in the chat about questions, and anyway, we have some time after the question and answer. Thank you, everyone.
Thank you.